Good morning. How's everybody doing today? If you're in the chat, just let me know. Say hi. Good morning. Good morning. Do we have any questions before we start off? Any questions? All right. So as usual, just jump in the chat anytime if you have any questions about anything. I'm trying to think if there were any particular issues by email, but I don't believe so. I think people were making their way through the quiz. And so just a reminder, make sure you're signed up for lab, lecture, and recitation. So all three of those sections. So I'll probably be emailing some people later today if you are not signed up for all three. And again, everything is just in that one Blackboard shell. So I just use the lecture shell, so you don't have to go hunting around or you don't have to worry about missing anything. You're already in the class. All right, so let's start off with where we left off. So we left off practicing converting. So let's warm up with these first two problems here. So converting 3 grams to milligrams and 7 meters to centimeters. And so I'll give people maybe a minute or so to work on this, and then we'll go over them together. And if you're in the chat and with us, of course, post your answers. And if you're following along later, of course, just take this opportunity. You can always pause if you need more time. All right, so let's go ahead and work through this. So we're doing 3 grams to milligrams. And so as a reminder, you should have this filled out. So this would help you. And again, I'll post notes today so then you can kind of double check everything. And grams is our base unit, so we can just use this conversion factor. We'll do 3 grams. And then for our conversion factor, we want milligrams on top, grams on bottom. And then there are 1,000. And remember, right, it's a small unit, so there has to be more small units in the big unit. So that can also kind of help you if you're having issues. All right, so now that gives us 3,000 milligrams for that question. And again, notice grams cancels, so we're left with milligrams. There we go. I was trying to pick a different color just so we can distinguish. Okay, so there we go. So now we're going 7 meters to centimeters. So again, let's set up our math. So what we know, so we're starting with 7 meters. Now set up our conversion factor. So we want centimeters on top, meters on bottom. And if we need, right, we can go back, we can look at this. So 100 centimeters in a meter. Let's put that conversion factor in 100 centimeters in 1 meter. Once again, meters cancels, multiply across, giving us 700 centimeters. And so remember, on an exam, you could also be given like a relationship that's not real. So I could make up different units, different relationships. So you just want to make sure you can understand this concept of, setting up kind of this dimensional analysis and doing unit converting. All right, let's skip down. So once again, I'll give you a few minutes or so to work on these. Well, let's at least do the first three maybe or so. And again, you can pause if you're watching later. Oh, just realized there's a problem. I didn't post the link. Should have gotten an announcement. I'll post another link. Or no, I'll post. Trying to give people a second to join. I think somebody's trying to join the lecture. All right, so I'll work on posting a link. I apologize for that. I just want a hard link in there. YouTube and a link. I apologize. Somehow somebody had my old Twitch link, which is kind of impressive. I thought I killed that. All right. So let's go ahead and go over these while we wait for people to join and find our stream. And again, if this is a bad time, we can move the time, but I know everybody online is taking, or actually really doing a lot of work. A lot of you guys are hard workers, so I applaud you for that. All right, so let's convert this. So 2.5 meters. And so again, right, we're just putting our conversion factor. And I want millimeters on top, meters on bottom to cancel. And then there are 1,000 millimeters in 1 meter. And so now we can just move our decimal place over. So 2,500 millimeters for that one. And so this is another, what I call maybe tricky one, or one where you might want to do a two-step conversion. Again, if you don't see it immediately. And so let's do this one by two different methods again. And again, we'll kind of see what people like. And it's totally up to you. And if you have a different method and you're getting the right answer, go for it. My only caveat is on an exam, you should definitely show your work. And the big reason why is so I can offer you partial credit. You'll be surprised at how often, there's a calculator typo or anything. So you don't want to just put the answer there. You want to show some work that I can follow. All right, so let's start off by what I call our two-step method here. And so that means that we're going to go from centimeters to meters to kilometers. And then we'll do kind of the one step. And so let's start off. So 4.5 centimeters. Let's go back to our base unit of meters. That means centimeters on bottom, meters on top. There are 100 centimeters in 1 meter. All right, so that works out. And so now we're going to go from meters to kilometers. So kilometers on top, meters on bottom. So there are 1,000 meters in 1 kilometer. And I'll just pull out the calculator so I don't get screwy on the zeros here. And so now we can do 4.5 divided by 100. Oops. Divided by 1,000. And so that gives us 4.5 times 10 to the negative fifth. The kilometers. And so now let's do it by our kind of one step method. Again, if you're not comfortable with this, don't worry. We'll just go over it. And now one step method. And so if we look back at what our factor is for both of these, so centi is 10 to the negative 2 and kilo is 10 to the third. So centimeter. And so you might be able to see right away that there's a 10 to the fifth difference between them. So I'm just dividing. And this is a good time to practice your mental math. So 10 to the third divided by, let's just do that, right? Divided by 10 to the negative 2. So you just subtract your exponent. So that's really a 3 minus a minus 2, which gives you 10 to the fifth, which is kind of making sense, right? So now, there's that same 10 to the fifth. Okay. And so we could write our conversion factor. And remember, it's the small units and the big units. That means there's 1 times 10 to the fifth centimeters in 1 kilometer. And so now that we have our conversion factor, we can set it up. And if you're quick with the mental math, you'll kind of see that, yes, this will give me the same answers. So we'll have to flip this, right? Because we want kilometers on top. We want centimeters on bottom to cancel out. And so just like we did before, right, we're dividing by 1 times 10 to the fifth. We get our same answer. So hopefully that helps. And again, whatever way you're comfortable with. So let's take another minute or so for these last 3. Give people some time to catch up and try to solve these if you haven't already. And again, if you're live, you can post your answer in the chat. I'll check it. Excellent. I see people have made it in the chat. Thank you. I apologize for having those bad links, by the way. Thought I had deleted them. This looks good in the chat, but let's go over it. So 77 meters to decimeters. So meters, decimeters on top. And there are 10 decimeters in 1 meter, which gives us what our chat got at 770 decimeters. Excellent. And so now let's do decimeters to millimeters. And again, this is another one that we could do by a 1-step or a 2-step conversion. So decimeters is 10 to the negative 1. Right, millimeters is 10 to the negative 3. So we could figure there's a 10 to the 2 difference between them. So negative 1, right, minus 3 gives us positive 2 there. So now we can write there 100 millimeters in 1 decimeter. And so we could do it that way. Or, so let's do our 2-step method. Let's go 37 decimeters. And so we want to go decimeters to meters, then to millimeters for 2-step. And so decimeters on bottom, meters on top to cancel. So that's divided by 10. And then meters back to millimeters. So there's 1,000 millimeters in 1 meter. So there kind of helps you see that 100 difference factor between them. And so then we should get for our answer 3,700 millimeters. And let me know, chat, if that's what you got. Thumbs up. Or if I made a mistake, also let me know. All right, so now let's go for the next one. And so this is another one that, you might know this relationship, so this could help, right? Some of you might know, well, I know that there are 10 millimeters in 1 centimeter, so that could help if you know that conversion factor. If we don't know this, so centimeters, so 10 to the negative 2, millimeters, 10 to the negative 3. So there's our factor of 10 difference between them. And right, again, we said small units into big units. So if there's a factor of 10 difference, we still get this. So that we got that conversion factor twice. Or We could also take this as a two-step conversion and go centimeters to meters back to millimeters. And so let's just write this out and then we'll compare it to kind of our easier factor. So 0.002 centimeters. So let's go centimeters to meters. The meters on top, 100 centimeters in 1 meter. Then back to millimeters. So 1000 millimeters in 1 meter. So notice those zeros cancel. That gives us our factor of 10 difference between them. And so now we get 0.02 millimeters. Questions about any of those or anything else that is cropped up? While I'm here live, you can also ask questions, lab, whatever people are having issues with. And for the lab, people found that there was a video, right? So there's a video of all the parts, so you can do them. I'll post a link in the chat. And they're old videos, admittedly. So from COVID, but they still work. If they don't work, of course, let me know. As far as I can tell, they still function. All right, let's continue on. So more math. And if you've looked at the lab or maybe attempted the quiz, as some people have, so this has come up with just questions. I think it's just people didn't look at significant figures. So now let's all go through it together and kind of what this means. And so this is really important, right? Because when we're in lab and we're measuring stuff, we're really limited in the precision of our measurements by our glassware. So it kind of depends, right, what we're using. And so that's why it's really important to select the right tool for the job, essentially. And so if we look, so conversion factors are treated as exact values. So all this means is that we don't include them when trying to figure out how many sig figs to report to. And of course, that would include all these other conversion factors. So even though some of these may be odd, so 1 inch to 2.54 centimeters, right? We don't include it in our sig fig. So all these conversion factors are not included. So they say they have infinite number of significant figures. And so now let's kind of look at, well, what are sig figs? And so this goes to, again, how you're going to report your number. And so let's just start off with kind of these rules and how to determine what is a sig fig. And so the first one makes a lot of sense. So all non-zero values are significant. Okay, so this number has 3 sig figs. That makes sense. And then this next rule, I call it our captive zero. And so this means, right, a zero is between non-zero digits. And so any zeros between our non-zero digits, those are significant. So this number has 4 sig figs. And so now let's look at the next 2 rules and we'll kind of summarize them, but let's first read them. So it says leading zeros. So placeholder zeros to the left of a non-zero digit are not significant. So looking at this number, only the 4 and the 3 are significant figures. And so if we look, right, these zeros are showing how small. And then our trailing zeros, so now it says zeros to the right after a non-zero digit are not significant. So looking at 7,000, if you were to write that number, that's only showing one sig fig. That would not be a very accurate scale, is what that's also kind of showing the reader or in your scientific communication. And then this number, so 32,040. So notice, right, it has a zero. That's what I call a captive zero. So these first four digits are significant, but then this last one is just showing how big. And so that's kind of the key, is those show how big. And then we can summarize this to basically say zeros showing magnitude are not significant. And so we'll kind of emphasize this again. So basically, what this means is, can you rewrite it in scientific notation to just get rid of the zeros? So, for example, this 7,000, right? We could just rewrite it as 7 times 10 to the third. Same number, but now we can clearly see we have one sig fig. And we'll also talk about how we can use scientific notation to give different degrees of accuracy. But let's finish with these rules here. And so zeros to the right after a decimal point are significant. And so if we look at this, right, this is kind of what I call this extra zero, right? So this other zero, this last one, is now significant because this was kind of unnecessary, right? They had already written out 50. We didn't need to write 0.0. But this is showing that, yes, I did measure this accurately. I was able to go to the 10th place. You know, we don't have a unit, so we don't know if it's grams or inches or what. But it's just telling us whatever equipment we had, I know that I measured it that precisely. Same thing with this number. So, right, it has 3 sig figs. So the 6 and the 2 zeros after the 6 are significant. Right, notice this first one is just showing how small. So that's not significant. So that's not included, but these are. So that's 3. Looking for questions so far. And so again, this is related to, you know, your glassware. So looking at this one, so this is a graduated cylinder. So this would be a more accurate way to measure stuff. This is usually how you measure liquids commonly on, if you're going for, you know, somewhat accurate measurements. But then there's other different equipment as well. So I'm just showing you some other equipment. So for example, this is a volumetric flask. And so this would be used in like analytical chemistry if you want it to be extremely precise. And so notice what the little summary says, that it is calibrated to contain a precise volume at a certain temperature. So what this means is it literally just measures one volume. So, right, it could be calibrated. So you can see these pictures. These are 1,000 milliliters. You know, you can have 10 milliliters, 1 milliliter, all different sizes, but they literally just measure one unit, each one. So these are pretty expensive, and you can, you know, even get a sense of the price. So this one is really expensive, but that's because they're, you know, made really precisely. They're calibrated. And then these volumetric flasks, so if we can click on them and see. And so notice they give their tolerance here. So basically how accurate they are. So this is telling you how precise you can measure this. So this would be relevant to your measurement. So right, so this is plus minus 0.8 milliliters at 20 degrees Celsius. So basically it measures 1,000 milliliters extremely accurately with a degree of error, right, of 0.8 milliliters. Kind of fascinating. And just let's go the opposite way. So less precise things would be beakers. So these usually aren't calibrated very accurately. And, that's something, if you wanted to come to our science fair and play with glassware, that's something you could do and get a sense of is accuracy and, what do these numbers mean? Because they're not really well calibrated, but again, you have to play with that in lab. Same thing with Erlenmeyer's. So these are good for heating liquids and sometimes running reactions. Again, it depends what you're doing. But again, not very precise for measuring. That's where all that comes in between. So if we go back to our graduated cylinder, which is kind of typically used, so these are pretty precise. So they have markings every zero point 0.1 milliliter. And that means that we can guess then. So right, notice, so this is 4 milliliters. So 4.1, 4.2, 4.3, 4.4, 4.5 there, the big one. And so we can guess out to the 100th place. So we know the 10th accurately, and then we'll guess out to the 100th. So that's our uncertain digit. And so in this case, right, it's somewhere between 4.5 and 4.6. And so we can just guess. So, they put 4.56 milliliters. You may disagree. You may think it's a little closer to 4.58 milliliters, but people are going to have different answers for that. So that's your uncertain digit. And so that's where we get, right? So then this reading, this measurement has 3 sig figs. So then when you go on to do calculations with this number, like calculating density, like you practice in your online lab, right? That's why you want to keep consistent with your measurements. All right, let's take a quick minute or so. So just figure out how many sig figs are in all of these examples here. And then we'll go over them, of course. And as usual, you can post your answers in the chat. I kind of know where people are. So let's at least start looking at them. So number 1, we have 54,000. How many sig figs in that one? And so this one is only 2. And again, this goes back to, can we rewrite it? And so 1, 2, 3, 4. So that would be 5.4 times 10 to the 4th is another way to write it. And so writing it this way clearly shows that we have 2 sig figs. What about 304? What do we get? So did everyone get 3 for that one? So now let's try number 3. What do we get? And this would be a good one to rewrite in scientific notation. And so if we do that, so 1, 2, 3, 4, 5, 6. So 2.10, right? Because we want to show, well, this is actually how accurate we're measuring. So 2.10 times 10 to the negative 6 there to rewrite this number. And so now this helps us clearly see that these leading zeros are just showing how small. So we only have 3 significant figures. Any questions? So now looking at number 4, and we could rewrite it. So this is only 2 sig figs. And then what about this last one? This one's actually a little tricky. And let's zoom in so we can look at it because it's not, I don't want people to miss it, right? So it says 10, there's a little period after. And sometimes you see this in textbooks, which is also why I bring it up. So how many sig figs? And so if you were thinking 2, you would be correct, right? And so this is weird. And so when we put a period now, so now this is showing, well, this 0 is actually significant. So I can measure to the ones place accurately. So this is 2 sig figs. But this might be a case where it's better to write it out in scientific notation, since, if you're writing it in a textbook, and that could be weird to have just a little period that people might miss. And so it might be better to rewrite it as 1.0, right, times 10 to the 1. And so now this is clearly showing that we have 2 sig figs. And now let's talk about that 7,000 again and think about all the different ways to report it, or any number, right? So if we're looking at, let's just say, right, 7,000 pounds, and we want to report it, and we had said, well, this is only 1 sig fig, so that would mean our scale, right, is pretty inaccurate. But this is where, right, we can write it in different forms, in different ways of scientific notation, and it tells you different levels of accuracy. So we could do, right, 7 times 10 to the third pounds. That's 1 sig fig. But what if we said, well, actually, we can measure to the hundreds accurately with this scale. So that could be 7.0 times 10 to the third pounds. So now we have 2 sig figs. And we can just go on like this, right? So again, it just depends how accurate your scale is. So maybe it's accurate to all of those digits, right? So you could do 7.000. Maybe it's even accurate, to the tenths in pounds. So 7.0000 times 10 to the third pounds. And so now that's giving us 1, 2, 3, 4, 5 sig figs. And so all the same number, but all just demonstrating different degrees of accuracy with your equipment. So that's where, you have to pick the right scale and then look at the scale. How accurate is that scale? So all that helps you figure out, right, how to report your data. And so now the next question is, well, now that we've figured out how many sig figs our number is that we got on our data, what do we do with it? How do we treat it with our calculations? And again, this is all just to make sure that the number that we're getting with these calculations is accurate enough, because we don't want to be misleading with our answer and basically saying like, hey, we know this to be more precise than we actually can calculate based off of our glassware. And so that's why it's important. Or, you don't want to go the opposite way either, where you lose accuracy in reporting your data. And so let's start with multiplication and division, because I feel like it's the easiest. And so if we look, so with multiplication and division, and we'll do some examples, but right now we'll just kind of look at the overview. So the least precise measured value determines the number of sig figs. And then with addition and subtraction, you can report to the smallest decimal measurement. So whichever one goes out the least is your limiting factor. And we'll, again, go through some examples. Let's get out our calculator for this one. Well, before we do that, let's just determine how many significant figures we have. And so we're and this is also a good reminder why you need to report enough sig figs when you're in lab or doing something hands-on is because, well, look at this scenario. So we have 3 sig figs here with our first reading. So this looks good. That's right. That seems reflective of a ruler. So we said most of them have tenths markings. So you could guesstimate the hundredth. But then this 4 looks like it was reported poorly. So you probably wanted to write 4.00, but this leaves us with 1 sig fig. And so let's just plug it in as well so we can see. And so we're punching it in. So 3.56 times 4. And so the calculator spits out 14.24. And again, that would be centimeters squared. So maybe we're getting the area of some piece of paper or something. But now, because of our 4 centimeter being reported so inaccurately, we can only give 1 sig fig in our calculation. Now we need to report to 1 sig fig, and then you just round appropriately. So in this case, right, we're at 14, so we have to round down to 10. So that's what was done here. So now we report 10 centimeters. Just watching for questions. And so now let's go through this one. So again, kind of looking at what we have. So we have 4 sig figs with this measurement, 2 with our 5.0. And so let's again follow along and punch that in. And so then calculator spits out 10.25. And so now we need 2 sig figs. And so that's where we get that weird 10 period, right? So if we're looking at it, we want to round to 2 sig figs. So we're at 0.2. So we have to round down to 10. But then, right, we have the ambiguity. How do we clearly report that it's 10 period with 2 sig figs? And so that's why they suggest here reporting to 1.0 times 10 to the 1 to again clearly show that this is 2 sig figs. And so now we have this problem. And so this reminds me of something in your homework because I did want to mention something because there's a few other kind of like ambiguities that may crop up from time to time or different scenarios. So let's look at this. And so this is I was trying to figure out what these units are. This is kind of weird. Because we're dividing by some centimeters. It'll probably be centimeters squared. We'll just do that or else it doesn't make sense. And so let's punch that in. So 4 point, I don't need to write the 0, just my calculator. But again, we get 5, but we only have 1 sig fig. So then we report 5 centimeters. Maybe I should just pull up your homework. There was a problem in your homework. And so your homework doesn't really say what scenario it is, but this is a good time to talk about the comparison. So I just pulled up the notes because it was easier for me. And so it's this question right here where it does the 12.3 grams divided by 5. And it didn't really say what it was, But it has a note here in the answer key exact. And let's talk about, well, what is it referring to? Where would you do this? And this is when we can actually count uh like very discreetly that there are five. So maybe this scenario in the homework could have been we're trying to take some average. So maybe we had, five kernels of popcorn or something, or five pebbles, right? And we had weighed them, so we got their mass of 12.3, and we were trying to find our average. And so, right, if you can count something discretely, so you can see it and count 1, 2, 3, 4, 5, right? You can hold five in your hand, then that's called an exact number. And so, right, that would not be included in your sig fig calculation. So the correct answer for the homework would be to report it to 3 sig figs. And so that's kind of the distinction that I was trying to make here, is if we had said, so now let's say different scenario. Let's say we're again trying to find some sort of average or divide this. Let's just say it was like a ribbon, right? That was 45.0 centimeters long, and you wanted to divide it by, 9 sections. Well, that's 9 discrete sections, right? There's no question that about there being 9. And so then you could report that to 3 sig figs of 5.00 centimeters. Does that make sense, the distinction? And so sometimes this is called like its difference in like population, again, whether you can discretely count, or is it something like, what if you were trying to do an average population? Like if you were measuring, the population of wild turkeys in Ashland or Jacksonville, wherever all these turkeys are that I keep seeing pictures of. But if you're trying to do a population, so that's where the sig figs of your number would matter again. Because then a population count is kind of inaccurate, right? If you're measuring like birds, for instance, where they're moving, so you're not quite sure, like, am I recounting? So maybe you're just trying to get the average in a certain area, like, oh, on average, there's, 9 turkeys in this, uh, square acreage area, whatever. So something like that, then the sig figs might come into play. But again, if you can count it, if you can see it, or even, let's say we caged up, or maybe not caged, I don't want to upset any animal rights people, but right, we took 9 turkeys and we got their masses and we got the average mass of our 9 turkeys, right? Then we clearly had 9 turkeys versus trying to get the average weight of an entire turkey population size. All right, hopefully that clarified. And if you have questions, again, just always reach out and ask, or ask in the chat, ask by email. And so then this last example is to emphasize that these are all conversion factors, right? So this is a conversion factor, conversion factor, conversion factor. So all these 3 don't matter in our sig fig. And so we only care about this number when determining how many sig figs to report to. And so that's 2 sig figs. And so that means we round to 2 sig figs. And so that means we have a 7. So we'll round up to 1.4 meters for that problem. Questions? All right, so now let's look at addition and subtraction. And sometimes I say that we want to write this in like elementary school. At least I like writing it like this because it helps me see better. But again, you don't have to. You just want to look how far out, how many decimal places is each one reported to. And so if we're looking at these numbers, so we have 23.467 plus 313.21. And so our first number is 3 after, and this is 2 after. And so this is our limiting one. So we can only report the two places after the decimal point. And so, right, you do your addition. So you get 336.677. But now we have to round the 2 after. And so with our 7 here, we round up to 336.68. And so again, same thing for this one. So that's why it's important to report accurately, right? We probably wanted to have those 2 zeros so we could report 456.32, but that wasn't the measurement we were given. So we're just given 457 with nothing after the decimal point. So we can't report to anything after. So we have to round it to 456. And so now this is just a scientific notation reminder. So just kind of showing, right, how to write things in scientific notation. Obviously, positive exponents, you add zeros. Negative exponents, you start going the other way, so to the left. And so again, you can see different ways to write all this. And so I'll post these notes. You can look at them. This should feel pretty comfortable to people. If it's not, you want to have some practice, play with it. Again, this course is designed for people of all math levels. So I'm not really sure where people are at. But if you need some help with this or you want to talk with me about this in more detail, I'm more than happy to help. I just didn't want to belabor the point here. All right, so now let's look at kind of temperature scales. So this will get us prepared for our course. And so we're probably familiar with the Fahrenheit scale. If you remember, water freezes at 32 degrees Fahrenheit. Maybe you got some freezing snow today. I didn't quite get that cold, at least in the city, but maybe if you're in other parts, you get some snow. And then water boils at 212 degrees Fahrenheit. And of course, while we in America find this pretty easy to recall, it doesn't really make sense or match up with other things and so that's kind of where the Celsius scale comes into play. If somebody just wanted to make it more easy, so right, water freezes, that's going to be 0. We'll set that at 0 so it's easy to remember. And then water boils at 100. Again, easy to remember. And so note with the Kelvin scale, so there's a couple of things. So does anybody know what the Kelvin scale is based off of? And basically, I'm kind of asking what is that? What's absolute zero? And so absolute zero, this is kind of a theoretical point, but this is the complete absence of motion. And I probably misspelled that. And so just like if you recall back to the first lecture, right, I mentioned even with a solid, things are moving, things are vibrating, right? Our electrons are still moving around. And so there's still movement. But at absolute zero, there would be no more vibrational movement. And all that would be stopped. And so let's see. I was just pulling up. I'll post a link to this article. See if this is a good one. This is a newer one than the one I usually. Oh. Okay, let's try. I'll just show this one. A little bit older, but you can, of course, try to see what the latest is. So this is one about the University of Cambridge where they're trying to get down really low. I thought there was some research out of MIT as well, but basically it goes into all these elaborate ways how they're trying to isolate it. Other articles. Here we go. Popular mechanics. Oh, there are a bunch of different teams. Hmm. I guess I was thinking about this research, but now it's relatively old at 2003, where they were half a billionth degree above absolute zero. So we'd have to probably look to see where the field stands currently today. So I'd have to read a little more detail, but I'll post that one in the chat for y'all so you can, look into it if you're interested. But, some of those articles just talk about, the different things that they have to do to get down to absolute zero. I think some of them also use like lasers to get rid of vibrational motion. It's quite interesting and crazy. But anyways, that's what our Kelvin scale is based off of, is this theoretical point of absolute zero. And like you were seeing with those research articles, of course, people are trying to get there as close as they can. But the nice thing about Celsius and Kelvin is that each degree increase matches. And so what I mean by that is, notice there's 100 degrees Celsius between freezing and boiling, and there's 100-degree Kelvin between freezing and boiling. So they scale the same, which means it's kind of easy to convert. And so let's just show the conversion. And so, right, it's basically the same. So we can convert by our temperature Kelvin equals our temperature Celsius plus 273. And sometimes you see this more precisely written as 273.15. But usually we don't measure temperature that accurately. So using 273 is just fine. And so again, notice, right, Celsius and absolute zero is negative 273. And so Fahrenheit obviously does not scale as nicely. And so there's 180 degrees, right, between freezing and boiling. And so I don't expect you to memorize these formulas. Again, all my exams and quizzes are open note. And so just kind of maybe write these formulas somewhere. If you want to grab a periodic table for me, I know a few people have inquired. So we can meet at school to do that. And maybe you want to write that on your periodic table. And so just make sure you know how to plug these in. So order of operations, if we're going from Fahrenheit to Celsius, first you do the parentheses. So you have to subtract our 32 and then you multiply it by 5/9. And then if you're seeing this in a textbook sometimes or another resource online, sometimes they may give you the decimal answer. So times 0.556 or something. And then 9/5, I want to say is 1.8, but let me plug it in. Oops. Yeah, so that's 1.8. So you might see it written different ways. So just be aware of that. And if you're going from Celsius to Fahrenheit, first you multiply our Celsius times 9/5 or 1.8, add 32 to that number, and then that gives you Fahrenheit. So not too bad with those questions there. All right, so now let's look at density. And again, you have some practice with your lab. And so we're looking, so density is just a ratio of mass to volume. And so, right, usually there's some sort of joke is what's heavier, 1,000 pounds of feathers or 1,000 pounds of stone. And if you get someone to fall into your trap, they picked a feather and then you go, ha ha, they weigh the same. But the whole point of that is people are thinking of density, right? That those feathers are less dense. And that's just referring to, again, their mass to volume ratio. And so that means that the units that we'll see, right, it could be grams per milliliter. You might also see grams per cc. So that's just going to be cubic centimeters. So centimeters cubed. And 1 centimeter cubed is also 1 milliliter. So that may be useful. And so let's also go over, if you haven't seen the triangle trick before, now's a good time. And so we can kind of rewrite it in this form. So density equals mass over volume. And so with the triangle trick, you cover up whichever one you're solving for. So let's say, so for this problem, we have 73.2 milliliters has a mass of 61.5. What's the density? So if you cover density, you're left with mass, and look, it's over volume. So mass divided by volume, which is admittedly what we just said, but this will be useful. So let's do that. I'm just pulling up my calculator. So mass, so 61.5 divided by 73.2. So that's, and then this is where we want to report. So they were both 3 sig figs. So we can report this to 3 sig figs. So 0.840. And that's going to be grams per milliliter. You could also see like kilograms per liter, etc. So there could be lots of, or kilograms per meters cubed. Just be aware, right? It could be any mass to volume units. So let's try this one. Again, use your triangle trick to help you. I'll give everyone a minute or so. So determine the volume of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeters cubed. So post your answer, A, B, C, D, E, if you have it. And so let's go over how to do it. So again, right, we could use our triangle trick. So let's see, it says determine the volume. So if I cover up volume, that leaves me with mass divided by density. And let's set that up. So I don't know why I put point. So 455.6 grams. And then we said divided by density. And so notice how these units work out. So centimeters cube goes on top since it's grams per centimeter. And then 19.3 grams on bottom. Notice how grams cancels. So that's kind of like your double check. So you have your triangle trick, then you got your dimensional analysis. So all that should match up. So 455.6 divided by 19.3. And so that should give us D 23.6 milliliters. And 3 sig figs is appropriate since we are limited by our density. And that's why I said, because you would have gotten centimeters cubed, but centimeters cubed is the same thing as milliliters. And on an exam for like free response, if there are free response questions, as long as it doesn't specify the unit, I'm not too picky about, what you report it as, or if you put it in scientific notation or not. I can interpret your answer. And so this last bit is just more of like a fun fact. It'll probably come up as vocabulary somewhere. And so specific gravity, so your book has it, your book has it as a more specific definition. So they say it's the density of a substance compared to water. So specific gravity, just more generally, could be any comparison. So any two ratios of densities. And so this is more like our book's definition. But in a lot of ways, it's kind of silly. But I mean, it's still a term we should go over. And so what does this mean? What is it saying? And so let's just look up. Let's take this substance here. So we have hexane. And so hexane has a density of 0.659 grams per milliliter. And so hexane's density 0.659 grams per milliliter. And then do people know what the density of water is? And why water is so beautiful? So the density of water is 1. I'll just put it in so we feel good. So this is the exact water density, but we usually just say it's 1. So 0.9998395 grams per milliliter. But again, essentially 1. So water is considered like our standard. Everything's usually compared to water. And so notice, right, it's just a ratio. And what ends up happening is your units cancel. So your density is still the same number since it's compared to 1. So you would say your specific gravity of hexane is 0.659. And again, notice, right, no units of that since it's just a ratio comparison. So kind of strange. I don't see it used too often, at least in my field, but it's in vocabulary, so it may come up on a quiz or test or something, so you should at least know this term. All right, I think I was just kind of finishing. We just have some practice problems. And of course, if there are any other questions, I'm more than happy to go over anything. So let's probably end just with these 2 questions. So I'll give people, let's start with the first one. So what is the mass of 6 centimeters cubed of mercury if our density is 13.5939 grams per centimeters cubed? And again, this is your time as well. So if you have questions about something, chime in on the chat. More than happy to talk about anything else. I don't remember anything burning from lab that people had questions on other than just issues finding the videos themselves. I don't think there's anything I need to cover urgently now, but that's also what I try to use this time for. So if I see that I'm getting a bunch of emails about the same question on the lab, I may address it live. And so let's go over this. If you can post your answer in the chat. And I just started by setting up our triangle trick. So I always like this. And so we can cover up mass. Oh, so we need to multiply density times our volume. And let's make sure that that works out, right, with our dimensional analysis. So this is good. It's always a check and a double check. So if I want to multiply those two, so my density is 13.5939 grams per centimeters cubed. I'm going to multiply it by my mass. And oh, that looks good. Centimeters cubed cancels, so that gives us grams, which is what we're looking for. And so now I need to pull out my calculator. So 6 times 13.5939. And so I get a mass of, and so we need to report it to 3 sig figs based off of this volume. And so that would be 81 point, and so I'd round up to 81.6 grams. Questions on that one? Now try this one. So converting the temperature of gold, so the boiling temperature, excuse me, of gold. So 2,966 degrees Celsius into Fahrenheit and Kelvin. So let's go through those. So let's start with Kelvin, just because that's easier, right? So we said temperature Kelvin equaled my temperature Celsius plus 273. Now let's add that. So 2966. Oops. plus 273. That gives me 3,239. And notice for Kelvin, you don't put degrees, you just write Kelvin. And so now let's go back to our formula. I don't remember the formula. And so we said to go from Celsius to Fahrenheit, so we need to multiply Celsius times 1.8 plus 32 times 9/5 plus 32. So that equals my temperature in Fahrenheit. So just plugging it in. So let's do that together. So 2966 times 1.8 plus 32. So I get 5,370. I'll round it to 71 degrees. All right, excellent. Any questions on that? So just a reminder, right, we do have our holiday. So in Blackboard, most of your assignments should be due on the 15th. So that's a Tuesday. So you have an extra day. And then I think I gave y'all until the Thursday to turn in your labs. And I'm not too strict about due dates. I just have the due dates there to keep us on pace for the course. And then I'll probably try to open up week 2 as well pretty soon and get that going for y'all. And I'll post these notes. And again, just keep in contact with me by email. Happy to meet in person or by Zoom. And yeah, thank you for being there in the chat. Really happy. Looking forward to a good winter term. And I will see you later. So I'll hang around on stream like I said I would. In case there are any other last minute questions, then I will officially end the stream. So thanks again. All right. Thanks again. Have a great rest of your week, and I will catch you online.